Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. All right. YouTube is working. Just one more left. Let's test on X. How's it going, Sataki? I think it's live on X too. Look at that. All right, let's test it on X. Testing on X. Testing on X. One more left. All right, X works as well. We're ready to start. Let me spit out this gum. Drink some water. Then we'll go ahead and get started. All right. Let's blow this horn to announce the session officially. All right, welcome everybody to another Hoopo stream. We're going to be doing something a little bit different today. We're going to be kind of doing something more open-ended, more broad. We're going to be looking at a variety of papers. I have almost a dozen papers pulled up here. And I kind of tried to group them into, I think, two big concepts that we're going to review today. So the first concept that we're going to be looking at today is synthetic data generation. And I've got 4 different papers about synthetic data generation. And then the second kind of bucket or concept we're going to be looking at is around flash attention 3 and some other kind of linear attention versus LoRA stuff as well. So some ideas around kind of more efficient inference, more efficient training, how the algorithms and the hardware kind of go together. So that's going to be the kind of second part. I also have some extra papers if we end up having a little bit more time. So that's the plan for today. We're going to be basically looking at all of these papers, a little bit different than what we've been doing usually, where we usually kind of focus on a single paper and go deep. I kind of want to try something different where I kind of do a more broader survey of all the different papers that came out this week and the past couple weeks and kind of see if we can get a better idea of the landscape by having a broader look rather than a more myopic look. How's it going, Khalil? So we're going to start with this one here. Maybe I'll introduce all 4 of the synthetic data papers. We have Scaling Synthetic Data Creation with 1 billion personas. This is from Tencent AI Lab in Seattle. Tencent is one of the bigger Chinese tech companies, but their AI lab is somehow in Seattle. I don't know how that makes any sense, but okay. We also have Meta with their own kind of synthetic data paper. This one's called Distilling System 2 into System 1. That's a reference to the Thinking Fast and Slow. Then we have Microsoft with AgentInstruct towards generative teaching with agentic flows. And then we have Video Star, self-training enables video instruction tuning with any supervision from Google Research. So you have 4 papers here on synthetic data, all released relatively recently. We have June 2024, we have July 2024, July 2024, July 2024, and we have all of the major technology companies representing here. We have Google, we have Microsoft, we have Meta, and we have Tencent. So all the big tech companies are working on synthetic data, and all of these papers seem to show very good promise, right? So everyone's working on synthetic data, and we're seeing results from it. So I think this is going to be a huge part of how we go beyond the limitations that we have right now. I think a lot of people are under this narrative that data is becoming the weakest link in the chain, that, okay, we're going to get to a point where we have enough compute, we have enough power generation to feed these giant training clusters, but will the quality of the data be good enough, right? Will we have enough data? We've kind of scraped all of the internet. We've scraped all of YouTube. We're already training on all of that. How do we push beyond that to get the next kind of 10x in data? And I think synthetic data is the answer to that, and we're seeing all the big labs pursuing it. So let's start with this one here. I think this is probably, out of all the papers we're going to read today, I think this one is the coolest idea, and really almost has me thinking about like ontological questions of like, is our reality just a simulation for generating data for some kind of like AI system that exists in some other reality? But all right, let's start here. So this work is about this idea of persona-driven data synthesis. So they create what they call Persona Hub, which is a collection of 1 billion diverse personas automatically curated from web data. So what the hell is a persona? A persona is a description of a kind of a person and a story, right? You could think of it like a background story for a person. And in this paper, they find a way of what they call text to persona, where given an arbitrary piece of text from the internet, they will create a persona from it, right? So for example, here's a random piece of text from some kind of machine learning paper, and then they create this persona, which is a description of a person, a machine learning researcher focused on neural network architectures and attention mechanism. Here's a piece of text from some kind of mobile game blog, or I don't even exactly know where this piece of text is from, and then they create this persona, a mobile gaming enthusiast who enjoys competitive multiplayer games, right? And what are we doing there? Well, we're creating these personas that represent different people. And once you have basically 1 billion of these different people, then you can use this as almost a vector of data augmentation, right? So then you can take any question or any problem and augment it by feeding in that persona, right? So here's an example. Create a challenging math problem with the following persona. And then you just plug in one of these billion personas and you'll get a unique math problem from a different perspective. So kind of a crazy idea, but it seems to work quite well. And they apply this kind of persona augmentation for things like mathematical and logical reasoning problems, instructions, texts, game NPCs, tools, and so on. Inspired by the observation that simply adding a persona to a data synthesis prompt can steer the LLM towards the corresponding perspective to create distinct synthetic data. And persona-driven data synthesis is versatile, scalable, flexible, and easy to use, potentially driving a paradigm shift in synthetic data creation and applications in practice. This to me seems like we've discovered a new form of text-based augmentation, very similar to the way that we discovered forms of image-based augmentation, right? Where we would left-right flip an image, rotate images, add Gaussian blur to an image. This is basically the text-based version of that, and you do it by pulling out personas, which I think is very clever because it comes from some kernel of intuition here that all the text that these LLMs are trained on are fundamentally created by individual people, and each of those individual people represents a different perspective on the world, the same way that when you take a cat image and you rotate it left to right, what you're really doing there is you're providing a different visual perspective of the same object. So the same way that you can provide a different visual perspective of some object in 3D space, and that object is still the same object, right? And in that way, you've now augmented your data set. You can seemingly do the same thing with concepts that are represented in text, right? So any kind of concept or blurb of text is written with some perspective, right? Where whoever wrote that text has some backstory, and that backstory, which is some inductive bias on like reasoning and word choice and all that stuff, you can literally switch that perspective to a different human persona, and now you have the same concept, but augmented by a different viewpoint. So I think this is a very clever idea, and they kind of blow this out of the water, right? Tencent has a ton of money, so there's a version of this paper where it comes out of some academic group, and like the experiments are like 1 GPU, and that's pretty much it. But that's not really what you see here. They generated 1 billion of these personas, 50,000 logical reasoning problems, 10,000 NPCs. So like they really kind of went all in on the scale here. But it really performed so well that they have a disclaimer here in the abstract where Persona Hub can facilitate synthetic data creation at billion scale. If this data is used as an input to query a target LLM to obtain its outputs at scale, there is a high risk that the LLM's knowledge, intelligence, and capabilities will be dumped and easily replicated, thereby challenging the leading position of most powerful LLMs. So this is pretty important, right? Because it basically means that, okay, if the intelligence of an LLM, right, when you're taking an LLM and you're using it to compress a huge text data set, you can elicit or almost like separate the intelligence in that LLM into these different personas, so that if you can ask the LLM questions through these different personas, you can more effectively kind of recover the intelligence and create a synthetic data set that actually represents the true variance of the distribution of the original data set that the LLM was trained on. So it's actually a more efficient way of doing what people were trying to do with something like Vicuña, right? Or any of these vision language models where you're using a GPT-4V to effectively label a data set, or kind of you're using a foundation model to generate some synthetic data to fine-tune a model, right? That's a paradigm that we see time and time again. But here, you're doing it through this lens of these personas, and it seems to be like a more efficient way of capturing all the variance in the original LLM dataset, which is really what you want to get to, right? It's like you want to create a dataset that is a compressed form of the LLM's dataset, but also sufficiently represents the diversity and the variance of the original dataset that the LLM was trained on, right? Because dataset scale is not actually the scale that matters, right? If I take a single labeled image of a cat and I just repeat it by 10 million, that's not a very strong data set, even though there's 10 million images in that data set, because it's just all the same example of the cat. What you really care about is the data set variance, or the kind of like diversity of that data set. You want a maximum, like a very wide distribution that captures all these different possible things. So data set scale only matters in that with scale, generally you get more variance. And this is a way of kind of creating that variance synthetically. How's it going? Aries and Eli KD25. Is the data all in Chinese? I'd imagine using multiple languages would also be good. So they do have some examples here in Chinese as well. So here you can see some of their let me see if I can scroll down. I saw it earlier. Yeah, here we go. So this isn't limited by language either, right? You can take any, I don't actually know how to read Chinese, so you have this blurb of language in Chinese, and then you augment it from the perspective of a different persona, and then you end up with the same blurb of text, but from the perspective of an avant-garde painter, or the perspective of a solo backpacker, or the perspective of a young aspiring firefighter, and so on, right? And like, why can we even do this? The reason we can do this is because LLMs are actually really, really good at this kind of role-playing, right? And why are LLMs really, really good at role-playing? Well, it's because what they're trained on is a diverse set of perspectives. So it's like we've realized that kind of a quirk of the LLMs that they're good at this kind of role playing actually ends up being one of the most powerful ways of doing text augmentation. And that type of augmentation is an incredibly powerful way to do synthetic data. So I thought that was a really novel idea. And yeah, I can't wait to see where people take this. Okay. Let's look at a different way of doing synthetic data, which is now this paper from Meta, the foundational AI research, I think they call it now. Instead of Facebook AI research, they renamed the F. Harry's saying this has been around since the beginning. Yeah, I mean, like, a lot of these ideas are recycled, right? Like, so pretty much there is no such thing as an original idea. I am a believer in that, right? At the end of the day, even all the original thoughts that you think you had, there's probably some other human that had those thoughts. There's definitely papers that are doing similar things, but like, I don't know, to me, this is the first time I kind of saw this presented in such a way that my brain clicked when seeing this paper, even though previous times it might have been shown the same exact idea and it didn't click. Deadly data for my undergrad project. I work on using role play to break the LLMs. Yeah, that's actually, it's a good point. That's actually how a lot of jailbreaking these LLMs works, is you get them to basically role play a persona that goes around the kind of safety stuff, right? I think there's a specific jailbreaker called like Pliny, which is a reference to like an ancient Greek character, but I would definitely check him out on Twitter. That's like the state of the art jailbreak guy. And like, if you look at the jailbreaks, it's like they're all basically that. They like try to confuse the LLM, get it to pull up some kind of weird persona, and then use that persona to basically do the whatever, like tell you how to make drugs or tell you how to make a Molotov cocktail, which is like kind of generally you're not allowed to do that, right? Okay. Let's go to this one, though, because this is a fundamentally different kind of way of doing synthetic data. This is Meta's paper. They call it Distilling System 1 or System 2 into System 1. System 2 is what they call chain of thought. So chain of thought is whenever you use an LLM and you give it additional token budget to basically think internally before it answers your question, right? So if you ask it a simple math question and you say, hey, what's the answer? And you gives you the answer, it's not going to be as correct more times than not than if you give it like a couple paragraphs to like think about the problem, quote unquote. It's not actually doing any thinking, right? At the end of the day, this is just like a statistical process that generates tokens, but allowing it to generate more tokens before it gives you the answer actually results in a better answer than if you immediately generated the tokens, right? And there is a similar kind of concept in humans. So there's a famous book that everybody at this point has read called Thinking Fast and Slow, where basically this psychologist breaks down the fact that humans generally have what's known as System 1 thinking and System 2 thinking. System 1 is this kind of like more immediate, kind of instinctual way of answering, and then System 2 is when you actually kind of stop and think about it in your head and kind of like create this MCTS kind of process where you're like searching down different trees in your head, right? So this paper is about using chain of thought to generate higher quality outputs and then distilling those higher quality outputs back into a language model. So very simple to kind of write this out in math, and I think it makes it more clear. So you have some input X, some sequence of tokens. You have an output Y, which is some other sequence of tokens. When you're using System 1, your System 1 will map directly from X to Y, right? So some System 1 model takes that X, and the model here, P, which is parameterized by some parameters theta, consumes that sequence of input tokens X and produces an output token, sequence of output tokens Y. System 2 is the same thing, but now you're also giving it the ability to output these intermediate output tokens Z. So now a System 2 system is again a model, but the model consumes the X and it can output Z and then Y. right? So that's really just the difference between System 2 and System 1 is that System 2 has the Z intermediate output tokens versus System 1 has Y. And really the concept here is very, very simple. What they do is they basically take all the input and output pairs that you generate with the System 2. So you feed System 2 a bunch of math questions, you let it do internal chain of thought, and then it gives you the answer. And then you effectively just discard the intermediate outputs and then retrain the model on the input and outputs of the System 2. So you're not using those internal chain of thoughts. You're just almost retraining the model as if it outputted the Y immediately, right? So rather than having to think through all of its crap, you're distilling it to the final answer. So you see here, System 2 gets some X, it outputs some Y, and then you use that as basically a new training data set for System 1. So they call this unsupervised curation, right? Where you're curating the output. You're curating a data set of higher quality outputs for a given input by using the model itself because of this chain of thought property where if you give the model the intermediate or if you give it the ability to do these intermediate outputs, then it'll have a higher quality answer. So this is kind of like this filtering, like the model generates a bunch of answers, then you use those to kind of filter, create a higher quality data set, and then train on that. And then you basically just repeat this loop. So this is more of synthetic data generation by iterative refinement compared to what we're seeing here, which is synthetic data generation via data augmentation. So two different kind of ways of looking at how to generate synthetic data, but both of them do seem to work quite well. Do I have any other highlights here? I think that's all the highlights there. Let's go into this one here. How's it going, Ed, Agam, Majetti? We have a question by Ed here. Because all the knowledge that we have is written by persona, we can restore all the knowledge by generating from the perspective of different personas. Yeah, it's almost like something that pops in my head when I see these personas is this idea of disentangling latent spaces, right? And it's like all the knowledge of this LLM is in some high dimensional latent space that's very difficult to understand. But what they're kind of almost suggesting in this paper is that one way to kind of disentangle and separate that high dimensional latent space is through through different perspectives of personas, right? So like, we're not necessarily hard coding that in our language models. It's kind of like an emergent inductive bias that comes from the fact that you're training on public web data that is being generated by billions of different people, right? I think that's more the way that I see it. It's like the different personas is an inductive bias of just public web data that's generated by humans, which is all public web data. I wonder if there's a limit to the distillation if you keep doing it over and over again. Yeah, so that's Eli Katie 25 talking about this more iterative refinement approach to synthetic data. And we have seen that, right? So there was another Meta Fair paper that we saw probably months ago at this point that was a very similar kind of idea of like using the output, refining the output, training on the output, and then using that new model to do it again. And it seems like at some point it kind of breaks down. Like at some point you start, you can only eat your own poo long enough, and then at some point there's no nutritional value in that, if you want to think of it that way. I think they talk about that in this paper here. They call it model collapse, right? So at some point you're kind of eating your own output so much that you kind of the whole system just kind of starts dying. But there's something here, right? I think if you maybe combine this type of iterative refinement approach with something like this, where you're augmenting it, that might help prevent some of this mode collapse, the same way that augmenting images is a way of kind of preventing collapse in that particular domain. Okay, but this paper from Microsoft research here is about synthetic data for post-training, using a powerful model to teach new skills or behaviors to another model, which they're calling generative teaching. So this creates both the prompts and the responses using only raw data sources like text documents and code files as seeds. And they create over 25 million pairs. So here is a figure where they basically explain what actually happens. They assemble a collection of raw seeds, aka textbook chapters, web articles, code snippets, and so on. They first transform the seed. Then they route it through a series of instruction creation agents to create a diverse set of instructions. And then they utilize another group of refinement agents to iteratively refine the complexity and the quality of the seed instructions. So here's the same thing, but with a little picture, so it's kind of easier to see. So you start from raw text documents or source code files that are used as seeds, right? And the use of the word seed there is the same use of the word seed that you'll see in like a random seed, right? Like a random number generator needs like some kind of seed which provides the kind of initial randomness that you then use to create the random number generator and start that process. So in this case, they're using just random documents, kind of similar to how here they create these personas from random documents, right? So they're sampling random chunks of text from the pre-training corpus, and they're using that to generate these personas, right? So the random chunks of text are acting as the seed in this paper here. In this paper here, it's the same idea, right? You're using these random chunks of text as the starting seed. Okay. Content transformation converts the seeds into an intermediate representation that makes it easier to create high quality and diverse data. Okay, so this process right here is almost identical to this process here. Right? So the same way that you're using this random chunk of text to generate a persona, and that persona is a intermediate representation that makes it easier to create high quality and diverse data, aka the same ecological niche that the persona is fulfilling. Once you have this quote unquote persona, or here they call it transformed content, it provides diversity, right? So the same way that those personas are providing different perspectives, here which ultimately provide more variance. Here you're also doing the same thing. You're using this transformed content to provide diversity. Once you have that diversity, then you run it through this seed instruction generation flow, which now basically generates the actual instruction type chat data set. So an instruction data set is something where you have this chatbot-like behavior where it's like user asks a question, robot answers, user asks a question, robot answers, right? Which is the type of data that you need to train your models at the very end, right? So pre-training is one thing, but instruction tuning is what you do afterwards in order to get an actual kind of like agentic, not agentic, but like chatbot-like behavior. So this step here, the seed instruction generation flow, is effectively analogous to this part here, right? Where you're basically using your persona to modify and create an actual little data point that you can use in an instruction tuning process. Okay, and then finally, in this one, they go the extra step of iteratively refining the instructions to boost quality, diversity, and complexity. So this paper here by Microsoft, this AgentInstruct, is effectively kind of like a combination of these two things here, right? Where you're both finding some way of using chunks of the pre-training corpus as random seeds to create these personas, or here the transformed content, using that diversity to generate instruction data sets, or here different modifications of some existing data set. And then in this paper, they actually go the extra step and do this kind of refinement process where you're kind of like iteratively going and improving the quality of that data set here by doing chain of thought and then throwing away those intermediate tokens, but I'm not exactly sure what they do here to iteratively refine. Damn, you guys are going off here. Aren't LLMs get plateau the same like CNNs? Data Titan, I think usually when you have a plateau, it's the result of basically you're maxing out on one of the things. So one of the things that you can max out on is the model capacity. At some point, the parameters, the number of parameters in the model, or roughly the size of the model, are limit the ability of the model to learn more things, right? So very small models have a smaller model capacity, which means that they just can have less representational capacity, less ability to store a lot of information in it. So that is a reason why you might hit a plateau, is your model's just too small, and even though you keep increasing the data, it's not gonna, there's not enough capacity of that model to learn from that or absorb all that knowledge. A different type of plateau might come from the data itself, right? So you can keep making a model bigger and bigger, but if your data set is a limited size, at some point you're going to start plateauing on the data set itself. So there's different reasons for plateaus, but this is these synthetic data creation strategies are ways of pushing past the data plateau, which is what a lot of people think we're currently on, right? A lot of people think we're stuck on the data right now. Like they think we've solved the GPU scale thing, right? Like NVIDIA is doing a very good job. They're making these giant data centers. We can train 100 times bigger models for 100 times longer. So we're kind of solving those plateau risks. But now the plateau that we need to get past is this data plateau. And I think that these synthetic data strategies are ways to go around that. DPD, drunken persona distillation. I don't know what that is. Actually, that's probably a thing. You could probably do. I bet you in one of these 1 billion personas is like a drunkard, right? I bet you there's a persona here that's like a alcohol enthusiast who enjoys drinking, and like they'll turn any math problem into like the drunk version of the math problem. So yeah, there's probably something there. You could probably create a drunk persona. Question from Aditya Hoopa. What do you think about reinforcement learning as community has moved on to mostly LLM and transformers? Is it worth it to learn that as a beginner? I would say reinforcement learning, it's definitely useful, but I don't know if it's necessarily the most useful thing for a beginner. It's very math heavy. There's a lot of history. So reinforcement learning has been going on for so long that there's like decades of terminology and work and techniques that like you need to get caught up on to like even just understand it. And I think a lot of the core ideas of reinforcement learning, like the MDP and like it just has some problems, right? It feels kind of like where it works well in like games and some other problems, but I just don't feel like, I kind of agree with Jan LeCun that the reinforcement learning is just going to be a cherry on top of this cake that is mostly unsupervised learning, right? So like most of the cake is going to be unsupervised or self-supervised learning, kind of like this, right? Kind of like this synthetic data generation where they're calling it unsupervised curation, right? Or something like this, where you're using an LLM to generate these personas as a way of creating basically augmentations to augment your data set, right? So like all these things don't require like a human in the loop, so they're kind of unsupervised or self-supervised, and if you want to think of them like that. And I feel like that is a better road to AGI than like reinforcement learning. So I don't know. I'm generally like, sometimes I'm pro reinforcement learning, sometimes I'm not pro reinforcement learning, but I feel like if you're just getting started, reinforcement learning is maybe not necessarily the thing that you want to start with. The process that is responsible for evaluating the quality of that synthetic data IMO is the bottleneck. Yeah, there is ways around that. So if you actually look at this paper, they do self-consistency of output. So we sample from this system 2 model a total of n times and accept the response that is the majority vote, right? So whenever you're using your system 2 to generate an output after your output Y, after you've generated a bunch of internal chain of thought, intermediate token Z, you can run this 100 times and then see, right, you're going to have 100 different answers, or maybe not 100 different, but you're going to have a bunch of different Z's and a bunch of different Y's, and then you can see which of these Y's appear most, and then that's probably the one that you want to use. So you can evaluate the quality of a synthetic data via simple ideas such as just majority voting. So I don't know. I think that this probably, you can keep scaling this. I don't know if there's a fundamental limitation to just majority voting. And actually that's kind of how we do that too, right? Humanity is itself a kind of self-improving kind of intelligence, right? Like just all of humanity together as one hive mind. Like you have a lot of different people trying to look at a bunch of different problems. Everybody's using their system 2 thinking from a different perspective. And if a lot of people end up in the same place and end up having the same ideas, then those ideas end up getting cemented into kind of our cultural knowledge, and then that cultural knowledge gets distributed amongst the new humans. So in a way, like, we're not even doing something very difficult either, right? Like humans themselves are just kind of doing the same kind of self-consistency, majority voting, unsupervised curation, and we just did that for like 10,000 years, and we discovered how to make rocks think. So, you know, I feel like it probably can lead to AGI. Okay. I used ChatGPT as a lawyer, and it gave me good UDHR, ECHR defense. I don't know what those terms are. Unfortunately, I'm not a lawyer. Any new thoughts on robotics since your last video with O? I think robotics is maybe overhyped a little bit. You know, I think that when you look at a lot of the demos, it still feels like demos. You know, it doesn't feel like we're at the point yet where the robotics is working and we just need to like scale it. It seems like we're still just trying to get it to work. A lot of the robotics approaches that people are doing now are simply just the robotics approaches from 10 years ago with a little bit of LLM kind of like magic sprinkled in there. But I think we're still missing a couple kind of core ideas before we have robotics figured out. So maybe I'm a little bit less hype on robots. I feel like a year ago, I thought that the robots were going to be just there in a year, but watching the progress of these different robotics companies, I feel like we still have at least 3 to 5 years before we have humanoid robots. How to generate the exact same prompt response every time if the exact same response is sent to LLM. So, I mean, the reason you get different answers from a LLM is because whenever it's getting the tokens, right? Whenever it's auto-regressively generating the next token, generally you're kind of sampling. There's some kind of randomness there, right? It's like you're not just greedily picking the best next token. If you were just doing greedy picking, then the robot would, or the LLM would give you the same exact string of tokens every single time. But by adding randomness when you're auto-regressively sampling the next token, you get a little bit of variance there. Okay. Question from Tacedon, do I think that transformers are that much better than alternate architectures, or is it more that transformers have already so much going in infrastructure and frameworks? That's going to lead into our second part of the stream here, so let's finish up this and then we'll answer that question. Okay. Video Star. Self-training enables video instruction tuning with any supervision. So this is by Google, right? So we saw a paper by Tencent, we saw a paper by Meta, and now we saw a paper by Microsoft, and now we see a paper by Google. So they're all working on this, right? This idea of like iterative refinement and unsupervised curation, you know, augmentation. Unfortunately here, they call it large vision language model. So the vision language model holy war is still in full force. You know, I think last week I actually conceded defeat. You know, for the longest time, I've kind of always thought that VLM is the way to call these things. But then we saw a bunch of papers that just called them MMLMs, multimodal language models. And I was like, all right, everybody seems to be using this MMLMs, so we're just going to call them MMLMs. But now you have another paper that's now introducing a new term, large vision language models, LVLMs. So I don't know. It seems like we still haven't decided what the fuck we're going to be calling these things, but all All right, I guess LVLMs is a little bit smoother on the tongue than MMLMs, but I think VLMs is the best out of all of them, right? It's short, smooth. I don't know. Whatever, maybe I go back to VLMs. But okay, we're talking about vision language models, large vision language models. And here they're talking about, they're going to introduce this video self-training with augmented reasoning, which they're calling Video Star, which cycles between instruction generation and fine-tuning, right? So this kind of same idea of like iterative refinement of the data using the model itself. And we can go into the actual figures here on how this is being done. So Video Star overview. Video Star utilizes any labeled video data set, blah, 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 action recognition, action quality, temporal action localization, right? Different types of video tasks. Internally, Video Star cycles between answer generation, where an LVLM is prompted to generate candidate answers. Okay. So in this answer generation stage, you simply just use an already trained model to answer some question about this video. So what is the action sequence in the video? Okay, first we see the man bending down, lifting a book, blah, blah, blah. Okay, so you're basically just using the model to generate some output. Then you go to step 2, label verification, where the generated answers are filtered to only those that contain the video labels. Okay, so you have kind of like a refinement process here where the videos themselves come with some text tags, right? So there's some supervision that has gone into this data set, right? Maybe at some point someone labeled the whole video with some text description, right? Or maybe they put these bounding boxes, and those bounding boxes have some specific category or class label associated with them. So you're using that kind of metadata for the video to curate the original answer that the pre-trained LVLM just kind of zero-shotted, right? So this is kind of system 1 zero shot. It just gives you some answer. You use the metadata to filter that answer. Okay, that's the label verification. And then 3, instruction tuning. The model is retrained on answers that pass the verification. So there is the closing of the loop there, where you basically use the filtered output now as a new data set to train the LVLM. So you see here the little robot has the little fire, which means that you're now using its own filtered output to train, right? So it's like very similar to this idea here, or this idea here, or all of these ideas, right? Where you're using the model's own output to train a new version of the model. And in order to make that output higher quality than whatever the model was originally trained on, you're using some kind of filtering, or here they're using the chain of thought as a way of guaranteeing a higher quality. And here they're using filtering based on the metadata associated with that video. Okay. I think there was something here that I wanted to show. Let me see if I remember. Is it this one? Unsupervised curation. No, it might have been this one. I'm just going through my notes here. Yeah, here we go. Okay, this is the one that I wanted. Out of distribution evaluation on math. I thought this was kind of interesting because this is like scrolling down in table 2 of this like 10-cent paper. So it's kind of like a throwaway table buried in the paper, but Claude 3.5 Sonnet is losing to GPT-4o, which is kind of interesting because it's like the zeitgeist and the kind of word around town, and even myself, like I've been programming more with Claude 3.5 Sonnet than I have with GPT-4o, and like I've kind of accepted that 3.5 Sonnet is better than GPT-4o, but here we have some results that say that no, it's not quite as good yet, right? So GPT-4o beating 3.5 Sonnet on some random arbitrary math bullshit. So I don't know, maybe don't necessarily believe everything you see online. I think we're starting to get to the point of these language models where especially for something like the arena evaluations, right? So like what a lot of people think is like the gold standard evaluation method for these language models is these like arena battles where people basically compare one to the other. But I think what these companies have realized is that you can game those metrics by having the model kind of sound better. I think a lot of what's the 3.5 Sonnet does, and the reason people like it, is just the way that it talks is a lot more... I don't know if I want to just say smart or intelligent, but it just sounds better than GPT-4o. So whenever people are sitting there and just comparing outputs, they're like, oh, I like this output better than this output, but it's not actually the substance of the output that they prefer. It's like the style of the writing. So I don't know. Maybe don't believe the arena scores, because sometimes it's not necessarily representative of performance. It's just representative of what people prefer. Okay. Damn, you guys are blasting away on these questions. Right, let me see if I can get some of these here. Do you know any, question from Aditya, do you know any OSS model that performs on-device speaker diarization for iOS? I cannot afford Pico Voice. I know there's like a Whisper implementation for the NVIDIA Jetsons, which are these little edge computers, but like I don't know about running models on iOS. I don't even have an iPhone, dude. I'm an Android guy, so to be honest, I don't know what the state of the art for on-device iOS Whisper is. TTS. Or STT, speech to text, which I think the official way people call it is ASR, speech recognition. Claude has a better persona. That's why people like it. Yeah, that's what I think, DM, as well. I think that, like, kind of what... I might go back. It's like now I might actually start using GPT-4o a little bit, because I think what I came to the same conclusion after seeing some of these things, that it seems like it's really just the persona, which is kind of weird, right? Because it's like the same thing happens to humans, right? So like if you think about historically, and even within a lot of like human organizations, like the king would have these like viziers or advisors, right? And a lot of times those advisors or viziers weren't necessarily the smartest people. They just sounded the best, right? So like you kind of have this like, you pick the people that sound good to you rather than necessarily the people that give you the best answers. Right? So the same way that humans do that, it's like we're doing that with language models now. So the language models are almost being improved in a specific dimension, which is like the pleasure that you get from hearing their answers rather than necessarily the correctness of their answers, which is like a weird metric to try to optimize. But I think it's going to get even crazier in the future, right? Because the same way that like social media figured out how to create extremely addictive content, because that's really what matters, I think that these LLMs, these AI companies are going to figure out a way, or like kind of optimize along that direction of kind of like creating an addictive friend, right? Some kind of like friend personality that like makes you want to hang out with them more, right? And like, what does that look like when you have like an extra decade of like optimization and billions of dollars being poured into trying to create the most addictive friend that you never want to leave, and you always want to have them around because they just give you the best stuff, and they're always like, they throw in a little joke just the perfect amount of time, you know, and they like start to learn how much you like to joke, how much you not like to joke, how dry do you like your content, how not dry do you like your content. They're constantly kind of like curating in that direction, because that is ultimately what people are going to make their decision on, whether they use 3.5 Claude or whether they use GPT, is going to come down to like the experience that they have hanging out with their AI. Google TTS runs well. Can you even use Google TTS on iOS? GPT-4o is not that good. I think it's because they went small with it. I think a huge part about GPT-4o versus GPT-4 is that it's probably much smaller and much cheaper for inference. So that's really, I think, GPT-3 to GPT-4, they definitely went bigger on the scale. But then once they did GPT-4o and GPT-4 Turbo, I don't think they were trying to make it bigger. I think they were just they did make it a little bit bigger, but I think they were really just trying to make it more efficient by making it a smaller model. So I wouldn't be surprised if GPT-4o is actually a smaller model than GPT-4. It's just because they didn't want to pay the inference budget for a giant-ass model, right? They needed to reduce the inference cost. So they probably, GPT-4o is actually smaller than GPT-4, if I had to guess. Okay. Let's get on with this second part. All right, so the second part of this stream is a second kind of bucket of papers that I think are all kind of related. And this is going to be learning to learn at test time, RNNs with expressive hidden states. This is one of the most popular papers over the past couple weeks. So I've mentioned this before, but the sources that I use for my papers are here, right? So you can go onto this GitHub that I have. It's called Hupo Docs, and this is where I put all the links and all the different stuff that I use for all the different streams. And here are all the different sources that I use. But this one here, Emergent Mind, I know this guy personally, and he's a pretty cool person. So, but you can rank it. So this RNNs with hidden states is like very popular. So I don't necessarily see the amazingness of this. This is basically the TLDR of this paper is just another kind of linear attention paper. So we've seen the RNNs, we've seen the XLSTMs, we've seen the Mambas, Mamba 2, right? Like, so there's a million of these different types of, not a million, but like there's a lot of activity in these kind of linear attention where you're basically the key difference between these type of models and the standard kind of transformer models is that the transformer has that quadratic complexity, and all of these have basically linear complexity. So the RNN is kind of like, I think, the umbrella term for all of these things, which is the recurrent neural network. But technically, an GPT is also a recurrent neural network because it's auto-regressively predicting the next token. So it's kind of looking at its own output. So that kind of, to me, fulfills the definition of an RNN. And even the author of the Mamba paper said this as well, that in the Mamba 2 blog post, he also said that actually, if you really think about it, like even self-attention is also a kind of RNN, right? Because self-attention can also be viewed from the perspective above, aka that it's kind of an RNN, except that its hidden state, commonly known as the KV cache, is a list that grows linearly with T. So if you think about a self-attention transformer as just an RNN, where the hidden state, rather than being fixed at a certain size, the hidden state, in this case we call it the KV cache, is growing over time, then now we're talking about the same thing. So basically it's like, does your hidden state, is that a KV cache, which means that it's growing over time as your context starts, as you go more and more and more tokens deep, right, into your context, that KV cache is getting bigger and bigger and bigger and bigger, right? So that's the kind of Achilles heel of these transformer models, is that that list grows with your the length of your contexts. But the benefit of that is that the hidden state explicitly stores all historic context without compression, right? So what do they mean there without compression? Is that this KV cache is like literally all the tokens, right? It's like literally the value for all of the tokens that you've seen up until then, versus in an RNN or in something like a Mamba or in something like this model or this RNN with expressive hidden states, you're compressing that, right? So in an RNN or in a Mamba, there's a state input dependent transformation of this hidden state, so that the hidden state is not explicitly every single thing that you've seen before. It's like basically this like kind of like compressed form of it. So like the benefit of that is that it's always the same size, so that it's going to be very efficient. But the negative to that is that it's compressed, right? So it's lossy, right? There's information that's going to be disappearing, and you might not be able to remember everything in there, making self-attention more expressive than RNN layers for long context. Okay, so that's Mamba's RNNs and LSTMs versus transformers in about 20 seconds. But what about this paper specifically? So what this paper does, which is kind of a weird idea, but like I guess it's somewhat original, is they make the hidden state a machine learning model. Okay, so I'm going to say that again. Rather than having a hidden state where you're kind of like adding stuff in and removing stuff out with kind of like a forget gate, kind of what like an RNN does, or maybe you're doing some kind of like input dependent transformation, which is kind of what like a Mamba does, right? What they're doing here is they're going to make the hidden state literally a little machine learning model, specifically a MLP. And they also try a linear model just to ablate a little bit. But really just think of it like that little hidden state is just a little 2-layer MLP. And then rather than updating the hidden state with these like forget gates and add gates or whatever the fuck this like RNNs are doing, they're literally pushing a gradient, right? So as you're moving token by token by token, you're pushing a gradient and changing the weights of that little 2-layer MLP that is your hidden state. So it's like your KV cache is a little tiny little MLP, little neural net. But this is also why I feel like this paper is secretly bullshit, is that in theory, this update rule, right, where you're pushing a gradient, here's your little learning rate, and you're pushing a gradient into the weights of that little MLP, in theory, that's an O of 1 cost, right? So it's like an RNN or like a Mamba where it's O of 1 compared to the O of T of the self-attention. But in practice, is it actually O of 1? And this is where I disagree with this paper. It's like, I don't think it's actually O of 1, right? Because pushing a gradient like this into a 2-layer MLP on every single fucking token, there's probably not, they're glossing over some kind of inefficiency there, right? I bet you that like this particular operation requires going to the CPU, then going into the RAM, then pulling something out of the RAM, then going back to the CPU, then going into the GPU, right? So like there's some, I don't exactly know what it is, but there's probably some weird order of operations here that results in this not actually being O of 1 and this being O of 1, right? And that leads us into Flash Attention 3. So Flash Attention 3 is the successor to Flash Attention 2. And what this is basically the implementation of these algorithms on hardware is there's a lot of nuance there, right? So like some people live in this kind of mathematical world where everything is just symbols and you're just doing these equations and you can come up with this like, oh, this is O of 1 and this is O of 1 and this is O of T and all of these are O of 1. But when you actually try to implement these things on hardware, like these GPUs, two things that seem like they're the same can actually have a huge difference when you go actually down to the implementation, right? Because these GPUs are very complicated systems that have different, they're storing intermediate values in these memory caches, which are ordered differently with respect to the actual tensor cores. And those memory caches, not only that, but they have different levels of precision, right? So like here, for example, they talk about low precision FP8, floating point 8 versus FP16, right? And this is now starting to kind of sound a lot like these quantization papers that we've talked about, where people are using these lower precision data types, even down to 4-bit, down to 1-bit, you know? You can lower the precision of the numbers or the parameters inside your neural net and get pretty good performance still, right? It's not going to be as good as using a higher precision data type, but this data type is basically kind of hard-coded into these GPUs, right? These GPUs, like the memory caches in them, whenever the person actually designed that thing that you're going to actually print into the silicon, like there's some data type that is designed to be used in that tensor core, right? And in that cache. So Flash Attention 3 is really just I almost want to say the beginning of a long history that's going to happen where people are going to be increasingly more and more and more kind of like making these algorithms such that they fit perfectly on this hardware, right? And that kind of goes to what was the question here that Tassadon asked, where do you think transformers are that much better than alternate architectures, or is it more so that transformers have so much infrastructure in frameworks and hardware? And the answer to that is yes, right? So the answer to Tassadon's question is that, yeah, the reason transformers are just way better than all these RNNs and LSTMs and Mambas is not because theoretically they're better, because theoretically they're actually quite bad. It's because these numbers aren't telling the real story, right? And even though you can say an RNN is O of 1 and this naive TTT, what is TTT? I think they define it here. Test time training layers, which is when you literally have a little MLP and then every single token is pushing a fucking gradient into your hidden state. It's not actually O of 1, right? Like if you were to try to implement this on a GPU, like the tiniest little thing where it's like, oh, okay, well now when you push a gradient, we need to get the value from this thing over here, but that thing from over there lives in a different memory cache, which is slightly further away from the memory cache here, which means that whenever we go and we pause things to go get that little value in that memory cache, now we have to wait 3 times longer. So now all of a sudden my O of 1 is like way worse than that. And my O of T is now actually way better because a bunch of people have come up with a bunch of ways of making the attention extremely efficient on the specific generation of GPUs that we have available, which right now is the H100s. Right, so here you have the H100 at floating point 16 compared to an A100. These are 2 different types of GPUs. I don't really know what this is supposed to represent. This is like the different caches, the tensor cores. But you can see here, for example, an H100 used in FP8 mode compared to an H100 used in FP16 mode. So there's so many little details like that that go into this that can make something way more efficient or way less efficient. All right. I feel like I'm falling behind on these questions here. Did he just print a web page as a PDF? I did. Yeah, this is basically the web page as a PDF. There is an actual paper for this. So they do have a link to the paper, but the paper doesn't have these diagrams. I really wanted these diagrams because they're pretty cool looking. You know, the paper is like kind of extremely dry. Works. Okay. I think there was one other kind of cool paragraph that I saw in this that I think is interesting to talk about here. Attention has GEMMs, which is the matrix multiplies. Those map moles between the Q and the K and between the attention P and the V, right? So basically, the attention mechanism is just these 3 things, the queries, the keys, and the values. The hidden state, right, like we're talking here, the hidden state is this KV cache. So this is the thing that you're kind of growing over time with as you're going through the context. But your matrix multiplies between these Qs and Ks, and then the output of that with the Vs are not actually the weakest link in the chain, right? So the problem is that non-matmul operations are much slower than matmul operations on modern accelerators. So we're sitting here, right, trying to think about ways to reduce the total amount of matrix multiplies, but that's not even what's slowing things down here. What's slowing things down here are things like special functions. Special functions, such as the exponential and the softmax, right, the softmax between this Q and the K, have even lower throughput than floating point multiply add. And they are evaluated by the multifunction unit, a unit separate from floating point multiply add or matrix multiply add. Okay, so as soon as you see this a function separate, it means that, okay, now if you want to do some other thing, now you have to go to this separate little part of your GPU, calculate that. Everything else is waiting while you're doing that, and then bring it back, right? So that's why I feel like this O of 1 here is a lie, is because I don't know for sure, right? I don't know enough about like GPU hardware to tell you for a fact, but something to me seems fishy here where this fucking gradient calculation here, I bet you it probably does something like this, where it's like it has to use some random shit over here, and then having to do that makes it like 10 times slower. So as an example, the H100 GPU has 989 flops of floating point 16 T flops and only 3.9 teraflops, right? So look at that. That's like 2 orders of magnitude less throughput for special functions. The situation is even worse for FP8, where the matmul flops are twice as fast, yet exponential flops stay the same speed. And you can see here, this is, so this plot here, this is a time plot, and this is showing you the operations that the GPU is doing. So you can see here, whenever there's a break, what that means is that you have to wait, right? So there's something over here that needs the answer from this thing here, right? So this GEMM1, or whatever this is, needs the answer from this GEMM0. So until this GEMM0 gets finished, it's basically waiting. And that's why your GPU utilization isn't 100%, right? Because a lot of times when you're performing these calculations on a GPU, there's certain things that have to wait for other things to finish, right? And that type of stuff is like, it gets really complicated really fast because it's not even a type of complexity that's like appealing, right? Like there's some complexity where if you learn the complexity of a certain concept, it stays, right? But like the complexity of this type of stuff is like ephemeral, right? Where it's like every generation of GPU is going to have all of its own little asterisks, and then the next generation is going to have a whole bunch of different asterisks. So like it's almost like a very, very complicated video game where they change all the like complicated talent trees like every generation, right? So like Flash Attention 3, like if we get to like whatever 300s, whatever the like generation 2 from now on, there's probably a bunch of tricks in here that no longer apply, and we're gonna have to discover new tricks to do that. So it's like a never-ending game of like figuring out clever ways of making all the different parts of these algorithms efficient on the current generation of hardware. And that kind of ties into this one here. This is just like a kind of a throwaway paper, but inference performance optimization for large language models on CPUs. I just liked this figure here where they just show you the custom kernel workflow here. So this is like some micro optimization that some guy figured out, right? Where he's basically realizing that, okay, you have your queries and your keys. When you multiply those here's your matmul, and then you feed that into the softmax. So that softmax is slow, right? That's what they're telling you here, is this special units such as the exponential for the softmax have low throughput. So this thing here, this softmax here is lower throughput than this QK. So even though we think we're optimizing by reducing the sizes of this K and V, like it doesn't matter. It's this softmax that's bottlenecking. But I think they do something fancy here with quantization. So you can see here that the query stays at BF16, the brain float 16, which is just a fancy type of float 16. But the key and the values are being quantized into int8, so that this key cache here, this KV cache, which is ultimately what's determining this O of T here, right? So the size of that KV cache is determining this O of T. But if this O of T, if we take that KV cache and now rather than storing it in BF16, we can store it in a data type that's way less than that, right? An int8. Now suddenly there's like a 1/2 right here, right? And if this one here has like instead of O of 1, it's really O of 1 times like an 8, right? Then these two might be closer than we think they are. It's your floating point 32 for this matmul here between the query and the key, which makes sense, right? This is the one, this operation here, I feel like is where all the kind of like intelligence happens. The queries times the keys, and then the KV times the queries, or the output of that times the values, which is why you're doing this in floating point 32 and this one in floating point 32. So this is like kind of the important part where you want the high precision, and then this part here, int8. Hijabs. While the point is valid, that's not what big O notation is meant to represent. It's asymptotic behavior. Yeah, I mean, I know what you're saying, Hijabs, and I agree with that, right? Like the whole point of this asymptotic, of this big O notation is like, okay, you get rid of all the stuff, right? So if this is O of 4 or if this is O of 8, we just say it's O of 1, right? If this is O7T, if this is O400T, we just say it's O of T, right? So like we simplify it so that we can compare this kind of asymptotic behavior of this algorithm. But what is the usefulness of that if in practice it always comes down to like what you're actually doing, right? Like how many actual flops are you pulling through this GPU? So like, it's not, I mean, I still think there's merit to doing this, right? Like there's a reason I continue to read these RNN papers and these Mamba papers, because I think there's something there. But I think that a lot of these people are like kind of deluding themselves a little bit by thinking that like, oh, just because we beat them in these kind of like big O notation kind of theory world doesn't actually mean that we're ever going to beat them in the actual real world where we actually have to run these on these GPUs, because these GPUs are being improved for attention, right? So it's like all the next generation of this H200 and then the H300, H400, right? They're making them better and better and better at this thing here, right? Versus I don't really see anybody trying to make hardware that is good for this, but I don't know. Maybe that's an opportunity. Maybe one of you can make a startup that is very, very good at this weird test time training where the hidden state is a little MLP. Can I explain Minikube? What is Minikube? Is that like mini Kubernetes? I've never even heard that. Let's see. Minikube. Sets up a local Kubernetes cluster. What's the point of this, though? Like, why can't you just use Kubernetes? It's just Kubernetes, but on one machine? IDK, bro. This seems more like a kernel issue. When you fuse the softmax with the GEMM, then you get much higher utilization. You're still limited by the SFU throughput. Yeah, I think that's... So what Hupes is talking about here is that all of these here, operations, like some of these can be fused. So you can see how here they mention that here, right, where they say there's a multiply, there's a matrix multiply, but the matrix multiply add. So like doing an extra addition with this matrix multiplication, it's almost like you get the addition for free. So like there's a lot of little things like that where like two operations done, you can actually you can basically have them as one operation. So like little, I don't know, it kind of goes to what I'm saying. It's like there's all these little kind of like one weird tricks, and these papers, like the Flash Attention 3 is effectively just a collection of one weird tricks that people figured out. It's like, here are all the like 700 different one weird tricks that we figured out to maximize the self-attention operation, which we're doing over and over and over and over again in all the different layers of this transformer on a H100, specifically for this specific data type. Did you see the recent paper about the FPGA implementation of matmul-free LM? Yeah, I did. I read that and it was pretty fucking cool, because the matmul-free LM paper, I think it was better than this paper, because this paper, it just basically stays in theory world. It stays in this like theory world where it's like, oh, we're O of 1 and therefore that's why it's good, blah, blah, blah. But the matmul-free LLM paper, like I think it was called matmul-free LLM. This one here. Like this paper, I give them a lot of credits because yeah, it's kind of similar to this, where it's like they're basically using some bullshit trick that like only really works in theory, but they go the extra step of actually fucking making. So they build a custom hardware solution on an FPGA. Like that is next level. Like if you make a paper where you come up with this new kind of like theory over here, like blah, 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 look at that, it's linear, we're saving some kind of self-attention, you see blah, 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 we're saving some operation there. But if you go the extra step to like literally make hardware to do this, which they do, they make their own hardware that is specific to their matmul free, I think you deserve a lot of credit. You deserve more credit than if you just do this, right? And granted, there's some complexity there, and I think part of this is that they also were partnering with a startup. Yeah, so like here they're partnering with this Luxy Tech here. So like really it's just the reason that they were able to do this is that if this guy wasn't part of this research group, then it would have just been effectively the same as this paper, where all they give you is just some theory. But by having this Luxitech guy here, that guy made this FPGA. I'm not 100% sure. I don't actually know who did what in this, but like going the extra step to show that, hey, here's our new cool, slightly more efficient way of doing intelligence, blah, blah, blah. Transformers are bad, blah, blah, blah. Quadratic attention, blah, blah, blah. But go the extra step and say, hey, we make an FPGA because you need to catch up to these guys, right? Like the Flash Attention 3, like NVIDIA is effectively doing this, but for attention, right? The same way that these guys are making custom hardware specifically for their matmul-free, you can really think of what is NVIDIA doing. NVIDIA is effectively doing that. They're basically making custom hardware for the attention mechanism, the self-attention. Snooks. Are there any ways to visualize the execution of quantized LLM models? I mean, I think for the visual, I really like the LLM visualization. You guys have seen me show this like a million times before, but this is like my favorite visualization. There's another one that I've seen somewhere, but I like this one because you can literally go through it like step by step. You can see that, you can hit play, and they like literally show you like, oh, this is, look at that. You do that, and then you matrix multiply there, right? But what they're not showing you is that in every single one of these steps, right, like fundamentally, like there's some actual hardware that is doing that for you, right? So like there's an actual memory cache that has some size that's performing this. So every one of these little operations, if you were to actually look at it on the GPU, if this doesn't fit perfectly in the GPU, there's going to be empty spots, right? So like one way of like visualizing kind of like how this works is like, I've talked about this as like the takoyaki, where like when you're making these, right? Imagine if you were making them and your tool was like, it had like enough room for like 12 of them, and you were making them 10 at a time. So it means that you're missing out on 2. So like the same thing is happening here, where in theory, like, oh, this matrix multiply should be the same as that matrix multiply, but actually in practice, it's like literally the specific data type you're using and the specific size of the tensors that you're multiplying matter a lot. Because if now, hey, you want to make 13 takoyakis, but your griddle only has space for 12, well, now you have to do it twice. You have to grill 12 of them, and then you have to grill one of them by themselves. So the little differences like that actually matter. So it'd be really cool if someone made a version of this visualization, but for specific hardware like an H100, where you could actually see, okay, I'm going to run this LLM with these specific head dimensions and this specific size of everything and this number of layers, and I'm going to see what it looks like when I run it on an H100, and I can see how many extra steps, or like how maybe over here it like misses out on the last 2 rows, which means that this step over here needs to wait an extra 1 cycle for it to finish those 2 that it hasn't finished before. But the complexity of that kind of visualization would be pretty intense, so I don't know if we're ever going to see that. In practice, you do a lot more max in attention than you do softmax. I'm not sure how big their SFU issue is versus a kernel fuse issue. Multiply. So you're saying that you do a lot of more multiply adds than you do softmaxes, but you still have to do the softmaxes, right? Like ultimately, I guess you're doing matmul there, you're doing matmul here. So like really the only softmax is in between here, right? So it's like right here. After you do the Q times the Ks, where's the softmax? It's somewhere here. Attention output? No, it's like in between. Here it is. Softmax. There it is. There's that softmax. See, there's that exponent. You see how there's a exponent here? That's the exponent that they're saying actually takes long. So it's not even the softmax itself, it's the exponent in the softmax. Exponential. Okay, I think we're kind of lost. Let's go here. Compress, then serve, serving thousands of LoRa adapters with little overhead. So it's just kind of related, but not related. I thought this was kind of a cool idea where these LoRas are basically like, this is the pure mathematical definition of a LoRa here. LoRa updates are parameterized by a pair of matrices A and B. So you have two matrices A and B. And given an input X to a layer, so some random transformer layer, right? The output of the LoRa updated model at this layer is W0 plus BA. So basically you're taking some model here, which would normally just take your weights and multiply it by the input X, and you're adding to the weights of that model this kind of like little update. So the way that I think about LoRa's, it's like a little bit of stored training, right? It's like a delta W. It's a delta of weights. It's a little change to your weights that you add it to your weights, and then your model is going to have a different behavior. So LoRa's were really popular. Maybe they're still popular. Maybe it's just kind of in my sampling bias. It feels like they're less popular now. But it's basically a way of having a lot of different types of the same model. So you have one version of Mistral. I think in this one they use Mistral. Do they? Am I making that up? Okay, I don't even know what model they use here. Yeah, it is Mistral. Okay, so they train basically a bunch of different variants of Mistral. And those variants are effectively just new little changes to the weights that you kind of add at inference time, right? And when you're serving a model to thousands of users, those thousands of users are going to want different versions of the model, right? So maybe you have one LoRa that makes this Mistral 7B better at math, and you have one LoRa that makes it better at French poetry, and you have one LoRa that makes it better at biology, right? You want to be able to load those little LoRa's in and take them out so you can serve all these requests very quickly. And that's what they're doing in this paper, is they're basically compressing these little LoRa's and then serving thousands of them with little overhead. So systems that serve real-time responses to queries, such as some kind of server that's running some product that thousands of people are using, and they're typing something into their phone. They're like, I want to use the French poetry one, and then they send that request, and they only have one server that needs to basically serve thousands of these little LoRa's. And the reason you can serve thousands of the little LoRa's is because really most of the model is the same, right? Most of the model is this W0 here, which is staying the same from time to time. So it's not like you have to load a new model into the GPU memory and then load a different model into the GPU memory. Most of the model is actually the same. Really, the only thing you need to load in and out for each different request is these little tiny matrices B and A, which are small because the dimension or the rank here is small. You see how the dimension of this W0 is dB times dA, versus here it's dB times Ri and Ri times dA. And this R is a very small number, which means that the total amount of numbers in this B and this A matrix are very small, which is why you can load them in and out quite easily. Compressing adapters individually via SVD, 500 LoRa's, compressed LoRa's, preserve performance while offering major throughput gain. And I don't know, maybe this is a way to tie back what we were looking here, right, with the synthetic data, right? Where could we use, right, like if synthetic, oh my God, I'm going all over the place here. If synthetic data gets to the point where now as part of any model training pipeline, you have effectively inference, right? So like your model training is no longer just limited by the throughput of just taking your pre-training data set and feeding it in batches into your model. Now your model training is actually a more complicated process where you're generating output with the model, filtering that output, and then using that to create a new data set and train, right? So like we were talking about the inefficiency of having to wait for one matrix multiply to finish before you can do the next matrix multiply, and how that leads to low GPU utilization, right? Now imagine how shit your GPU utilization is going to be when your training process has to wait for some model to output some stuff and then filter that stuff and then blah, 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 and then generate the data set for you to actually train on, right? So like as pre-training and model training gets more complicated because synthetic data generation with the model itself becomes a core part of the training workflow, then maybe I could see kind of a weird combination of basically this, serving thousands of LoRa adapters with little overhead, and this, scaling synthetic data creation with 1,000 or 1 billion personas, right? Where you take the model itself, you create a billion different LoRAs of the current model for different specializations, different personas, then you generate or perform inference with all those little LoRAs, all the little LoRA versions of the model, use that to generate the next kind of corpus of instruction tuning data, which you then use to instruction tune the base model, and then repeat that whole process. Which sounds pretty complicated, but I don't know. All right, let me see. All right, I think I'm losing everyone here. So let's go into some of these throwaway papers. I didn't really have anywhere to kind of categorize these. These are kind of just all over the place, but I thought these were kind of cool. So we're going to start here with MuBench, Vision Language Benchmark for Microscopy Understanding. I thought this was kind of cool, where recent advances in microscopy have enabled the rapid generation of terabytes of image data. So I didn't realize this, but I guess that microscopy, which is like this type of shit where you're like looking at little cells with a microscope, I guess at some point the kind of just general automation and robotics got good enough that you can probably just like move a little slide and it just takes bunches of pictures. So like we have the ability to generate terabytes of data for this type of microscopy stuff. But now the question is, okay, well, how are we ever going to get people to label this shit, right? Like that's way too much data to label, right? Well, what if you don't need to label it, right? What if you basically do what they were doing in here, right? With this Google paper where, hey, you can use the metadata of the video to filter and refine the initial zero-shot output of a VLM and then train that VLM on that refined output and you'll get a better VLM. So you combine that with this, and now we might have a self-improvement loop for microscopy VLMs, right? So anytime you have this automated microscopy process that is, maybe it has like one particular piece of like tissue and you're like taking hundreds of pictures of that, right? You don't have the ability to get an expert human to label every single one of those hundreds of automatically taken pictures, but you have some metadata associated with each of those pictures. You can use that metadata to basically filter the zero-shot initial guess of some VLM, then use that to create a data set and then train the VLM on that data set, and now you have a better VLM. And then you do the same thing with the better VLM. And then you just keep doing that over and over and over again. So I could almost imagine like a farm in the future where we're going to have some warehouse with just hundreds of these robots that are just sitting there just taking pictures, just cutting random biological material into slices and then just randomly taking pictures of it. And then you have VLMs that just randomly zero shot and give you, this is what I think I'm seeing. And then like some other VLM filters that out, retrains the original VLM. And then that farm of 1,000 robots just sitting there, just automatically taking pictures of the biology slides or microscopy slides is effectively just like almost like a data farm that doesn't even need a human in the loop, right? There's no humans in the loop there. It basically just self creates its own data to train itself to then self create its own data. So I'm starting to see these everywhere, guys. I'm starting to see these synthetic data kind of self improvement loops. Like they seem possible in a lot of different places, and I feel like this flywheel, this self improvement flywheel. Once we have that, we're going to make a lot of progress very quickly. There's something else in here. I think there was something here which I thought was cool. Yeah, I thought this one was pretty good. Look at this. GPT-4o is blowing everything out of the water. Like, look at this. GPT-4o, 62% compared to Biomed Clip, which is like some clip VLM that's specifically for Biomed. It's like 20 points more. 30, 51, 38. Like, GPT-4o is not trained on any of this shit. It's not trained on any of this microscopy. As far as I know, it's there's none of that in there, but somehow it's just like it's so good. Guys, like it's out of control. I don't know what they did with that GPT-4o, but it's still very good. Still using GPT-4. Question from 7. I remember Llama 3 taking a much bigger performance hit for quantization than Llama 2. Has there been any such observation with LoRa's? Yeah, so when we read the Llama 3 paper, I don't even think it was the Llama 3 paper. I think it was like another paper that was published basically as soon as Llama 3 came out, but they tried to quantize the Llama 3, and it wasn't as robust to quantization as the Llama 2. LoRa's are kind of different. LoRa's are... You can combine LoRa's with quantization, and we read papers where you can use LoRa's to make up for some of the loss in performance that you get from quantizing a model. I don't know if I've seen a lot of papers where they quantize the LoRa's themselves, but, you know, that's kind of what they're doing here. You know, they're kind of like compressing the LoRa's, so there's probably similar kind of intuition there, where the same way that if you quantize a model or use a lower precision data type for the model parameters, it's going to lose a little bit of performance. I bet you the same thing happens with these LoRa's, where the LoRa's, as you compress them more and more, as you reduce the size of this R, the capacity of the LoRa basically also decreases. So it's probably a similar story. GPT-4o was probably trained on microscopy samples from academic papers. Okay. You're probably right. I think that's probably right, Hijups. The reason it's better is not because there's some magic there. It's because they actually scraped all of YouTube. And whenever they scraped all of YouTube, there's probably millions of hours of videos on microscopy. So it's somewhere in the data set. I got to agree with you on that one, but this is like a significant bump in performance. Colorectal tissue. How do you get colorectal tissue samples? That's got to be pretty gnarly. All right. PaliGemma. This is Google releasing 10th July, so literally today. No, 2 days ago, their own little tiny VLM. So 3B, it's a very small VLM. It's built on top of SIGLIP, which is basically like Clip, but slightly better if you want to think of it that. It's not actually better, but, you know, it's better in their own way. Kind of very similar to all the other VLM architectures we see, right, where you basically just have the vision encoder, then you have some connector. In this case, they're using a linear projector. We found that more complicated alternatives do not provide a clear alternative. So then you just have a bunch of vision tokens. You concatenate the image tokens, and then you use some pre-trained language model, in this case Gemma, which I think is Google's kind of like open source offering, right? We saw Francois Chalet of Keras kind of spearheading that, or at least shilling it. So pretty standard, nothing to see here. I don't feel like there was anything super interesting here. They don't even show you, like, I didn't find a table where they compare to the other ones. Like, that's really the one table I wanted to see, is like, how do you compare to GPT-4o and to the other vision language models? But they didn't. It's kind of like a weird paper. They just kind of like say, hey, we also did a VLM that's small, but is it good? I don't know. Different sizes. Oh yeah, there was one thing here that I thought was kind of cool. Where is it? Here it is. So this is the size of the image. And you can see here that for some of these, there's actually a huge difference. So look at this, the difference between 224 by 224 and 448. So twice the image size. You can actually get a significant jump there, 28 to 40. So it's these, like, it seems like a lot, some of these VQA benchmarks, if you just use a big image, you can get a pretty significant boost in performance there. Maybe they bought NHS data. NHS is like the British healthcare system, right? I think there's kind of like a weird advantage that the UK has because they have government provided healthcare. I think there's only one entity, the NHS, that has all the data. So if you can just figure out a deal with the NHS, you can use all their data. Versus, like, I think in the US it's probably more fragmented than that. No one owns all the medical data. In the US, the medical data is like distributed over a bunch of different entities. So getting all the US medical data is going to be much more difficult than getting all the medical data whenever it's kind of all collected under one entity, like you see in these kind of more government kind of socialized medicine. So yeah, I think that's really like this dude. You guys remember this dude, Suleiman? This is like the reason this motherfucker is important, right? So I don't think this guy actually has like any. Yeah, like this guy dropped out of college in 19. I don't think this guy's like technical, but like he has. He worked for the UN. Where exactly am I looking at? Yeah, Suleiman launched DeepMind Health at the Royal Society of Medicine. DeepMind Health builds clinician-led technology for the NHS and other partners. DeepMind revealed research collaborations with healthcare organizations. So what is this guy's competitive moat? The competitive moat that this guy has, and the reason that Microsoft got this guy is because he's the key to the healthcare. I might have said this before, but it's like, this is my like conspiracy theory, is that this guy, like what this guy, whenever you hire this guy, like the reason they want this motherfucker is because he can get you the healthcare data. He has the personal relationships with all the healthcare providers in the UK. So if you hire this guy, you get all the healthcare data, which is worth a lot. So, but it's kind of, you know, I feel like it just puts a bad, like it's, I just hate that society is there where it's like the person who gets the healthcare data is like some person who's been like developing these relationships and like knows these people personally, right? It's like, I wish it wasn't the case, but that's how society works, you know? The people with the connections are valuable because they have those connections. All right. I'm going to get in trouble one day for talking about random people conspiracy theories like that. All right. I think there's two more. Got like 20 minutes left here, so let's go over these two because I thought these were kind of cool. These are completely unrelated to almost anything we've talked about. This is live portrait, efficient portrait animation with stitching and retargeting control. This one was also very popular. Like, look at this. Over 6K stars on GitHub, bunch of X, Twitter views, and I think there's also videos that people have posted on this as well. Yeah, look at this. Look at all these videos that people made on them. So people love it. So what is this and why is it different? So the difference between this and other kind of attempts at this kind of portrait animation is what they're doing is they're implicit key point based versus previous works. I think usually what you saw was this kind of like in painting where you would basically just like erase and then use a diffusion model to replace, erase, use a diffusion model to replace. But here they're kind of almost taking a step back and going back to these like kind of like key point representations and then using that to warp. See this warping module here? So it's almost like this is like old school, a more old school kind of approach than some of the more modern papers, but it seems to work quite well. I don't know, this is like your classic kind of bag of tricks. Maybe not bag of tricks, but like Lego block paper. I think people have called this before, where you just take like 17 different little Lego blocks and then glue them all together, and then you get one final demo. But the thing with Lego block papers is that if your demo's fucking good, then there doesn't need to be a single original idea in this. If the final demo is cool, then you can have a very, very popular paper even without any kind of original algorithmic novelty, just because your final product is good. But the problem with these kind of papers is that if you just glue a bunch of Lego bricks together and the final result is shit, no one's going to care about your paper. So a little bit of a gamble, but I guess in here they paid off for them. Stitching and it's even more complicated. Look at this, guys. This isn't even the whole thing. This is just the first stage. And then you got the second stage. Holy shit, dude. Take the image, you extract features for the appearance, and then you extract the motion. So you're separating the features and the motion. The motion is itself three different things here. You have key points, you have a head pose, which is some rotation matrix, and you have a deformation expression. So these are all kind of like human designed representations of like the face. The problem with these type of things, though, is that like it probably does not work well for something that isn't like a centered human picture. So because it doesn't work well for something that is a centered human picture of a face like that, that means that you have to run some kind of bounding box detection to crop out all the different faces. So then because you have to run a bounding box detector like that, what happens if you have two faces right next to each other? Then that's going to mess with your thing and then mess with this. So these Lego block type papers, it's like, it can be an absolute nightmare. And there's going to be a lot of edge cases, but it seems to work well. Lip retargeting module, eye retargeting module, stitching module. You have a warping module that's being fed. What is FS? FS is probably some kind of feature vector. Here it is, appearance feature volume. FS, which is then being used later here into this warping module, which is frozen. God damn. All right. Categorical codebook matching for embodied character controllers by Meta Reality Labs. The video for this one was cool. But this is also kind of like I think this one is maybe a little bit more merit from an algorithmic novelty perspective. They use basically these code books, kind of like the VQ VAEs. Each codebook vector has some number of rows, some number of channels. A continuous latent space allows wrong interpolation. So rather than taking some input command of like, hey, here's where my controllers are, here's where my headset is, let me project that into some continuous latent space, and then I can sample from that continuous latent space and then project back out into like the key point skeleton for the pose, right? So like ultimately you're mapping some input pose of the controllers in the headset into some output pose of like the full key point skeleton of this human, right? So it's like a mapping problem. You're going from this input to this output. And rather than doing it through some compressed latent space that is continuous, which allows for wrong interpolation. So wrong interpolation there means that maybe when you trained this latent space, right, you're basically training that with little data points. So you're basically peppering this latent space with points. At actual test time, you're going to feed in some unseen input. It's going to project into that latent space into some point that's really an interpolation of a bunch of points that is seen during training. And when you take that interpolated point and try to project it out into like an actual key point skeleton, you might get something funny and weird. So by discretizing or quantizing that latent space into like a code book, which is like, hey, we're going to limit basically take that continuous latent space and turn it into like a limited set of possible motion sequences, then you fix some of the issues that you get with interpolation. I don't know, props to whoever made this paper, probably this guy. Like, really nice videos, really cool figures. Let me see if I can find the... Yeah. Show me the videos. Look at that. That's clean. I'm looking at the feet. You see the feet? You see the feet rotated out. Like, that's fucking crazy. Like, look at the way the feet are pointing, and then when he rotates, the feet point the other way. Right? Like, there's no foot tracking here. Like, the only input is the position of the headset, which is a 6th off, and then the position of the controllers, which are each 6th off as well. So you have basically 6 plus 6 plus 6, and that's it. And that's giving you all of that. You're turning that into like literal foot positions. Some of it's a little bit sloppy. You see how sometimes the foot goes like in to the ground. All right. Yeah, it's pretty cool. Ed, I love this type of shit, but... So, like, maybe, like, a meta point here. It's, like, these type of papers are cool, but, like, if you're really trying to, like, learn, these papers can be overly complicated, right? Because these type of things, it's, like... I don't even know if I want to go into that rant. Let me not go into that rant. I was going to go into the rant of, like, wasting brain power trying to, like, learn very complicated, like... Lego block papers, but I'll leave it there. Ogram. I used Docker Ollama to analyze 100 batches of Glassdoor reviews for stress-related immune system damage. Okay, so Docker is a containerization, basically a way of running or isolating the dependencies for something. So you're running Ollama inside Docker. 100 Glassdoor reviews. Glassdoor is like a employer review site, so you can basically see whether employees don't like certain employers. For stress-related immune system damage. So it's like sentiment analysis on Glassdoor reviews. Okay. All right. Nobody likes reading papers with complicated, long architectures. Yeah, it just feels like it's like I'm like... The way I describe it is it's like... Imagine if you like bought like a printer from like 2004 and then like opened up the instruction manual and just like started reading the instruction manual for like a printer from 2004. You know, it's like there's a lot of information in there and it's very dense and it's very technical. And if you read it, you can feel like you're learning something, but you're really just learning a bunch of nonsense. It's like you're cluttering your brain with a bunch of kind of like overly specific details that don't really like generalize beyond that printer from 2004. So it's like these papers are kind of like that, right? Where it's like you're sitting here and you're going to read this paper and you're going to understand the details between these like fucking 400 different losses that they use for like the expression deformation. It's like you're going to actually just spend a bunch of like juice, like a bunch of compute on learning this stuff, which isn't necessarily going to improve your ability to generalize to new things. It's like, I don't know, sometimes you want to think of your brain and your entire life as like a limited compute budget and like make sure that what you're spending your compute on is an efficient use of time. Right? Like this is actually why I have a hard time reading things like, for example, Game of Thrones, where it's like in Game of Thrones, the books, right? There's like literally hundreds of characters and like there's all these relationships between the characters. And like whenever I read those types of like fiction books that have like very complicated characters and worlds, I'm like sitting there and I'm being like, every time I remember one of these character names, it's actually pushing out some other factoid in my brain that maybe is more useful. So I don't know, like it kind of like triggers me whenever I'm like learning shit that I know is not useful. Or like this also happens with programming, where like maybe I'm using some kind of library and I'm like sitting there like learning these specific details associated with this library, and it like slowly drives me insane because I realize that like as I'm learning this library, I'm like slowly becoming worse at some other thing that maybe is probably better. But I don't know, I'm perhaps a bit neurotic in that sense. All right, guys, I'm tired. I don't know what else to talk about. I hope you guys got something out of this. Definitely give some feedback. I don't know. Maybe you guys like this new format. Maybe you guys want me to go back to the format of just picking one paper and diving deep. But I feel like going like this in a kind of a more broad way allows us to kind of talk about kind of the bigger trends that are happening, because I think that's kind of the cooler stuff. So, you know, in summary, what do we have here? We have all of the big tech companies are playing with this idea of synthetic data, right? There's different ways to think about synthetic data. You can think about synthetic data as kind of augmenting existing data sets of like, hey, how can we create augmented synthetic versions of already existing data set, which is, I would say, kind of more this persona of like, hey, let's just augment this, look at this concept or this data point from a different view, which is personas. Or you could think of it more kind of like these papers do, where they're kind of like refining. So, hey, let's use chain of thought, or let's use some metadata to refine the output and then train on that refined output. So that's kind of this type of stuff. The other kind of trend that we explored was this idea of kind of, there's a lot of activity now on this, like these linear attention models and different algorithms and model architectures that on paper seem like they're way better than transformers, but in reality, they're really not, because there's so much activity happening on the optimization of how do you actually run these algorithms and models on the hardware. And the hardware is so specialized for specific operations and a specific ratio of certain operations to other operations, and like specific sizes of different parts and chunks of the model, that like, even though in theory these are better, they're really not, because of the way that the hardware is evolving in tandem with these models. We saw how some of these synthetic data generation loops are starting to be used in not just LLMs and making a foundation model that's better, but actually in completely different fields, such as microscopy, right? So this is, I think, huge, right? Like self-improving loops in different areas. Google releasing a small VLM, and then we looked at like some Lego block papers where they just glued a bunch of shit together and got a cool demo. Cool VR demo, and then cool kind of like, what would you call this, live portrait demo? But yeah, hope you guys found that useful. Any recommendations on GPTs for understanding papers? I would just use Claude and ChatGPT, just plug in the section in there. Can we do one paper deep dive when it's an important paper like Llama 4? Probably, yeah. I'm building RL-based CPU optimization. Point me to any resources that can help me. RL-based CPU optimization, so kind of like a neural architecture search, but using reinforcement learning. I would think the geometry math Google, the fuck was it called? Alpha Geometry? Yeah, it's like AlphaGo, but for solving these Math Olympiad problems. But these Math Olympiad problems are, you can solve them in this kind of like proof language, which is basically like a domain-specific language for math proofs. So in a way, like CPU instructions are kind of their own similar kind of programming language, right? So like you could probably take some ideas from here. I don't know. That's what I would recommend. Can you do a similar session with CVPR papers you found interesting? Yeah, I think we kind of did that last week. Have you seen any thoughts on the new Copied Act? I don't know what that is. What the fuck is Copied Act? U.S. lawmakers propose bill to understand source of AI-generated deepfakes. I just have like fucking zero interest on this. What the fuck is this? Detection of synthetic content, watermarking content. So it's basically like requires watermarking. Yeah, I don't know. I don't like, I just don't think government is good, guys. Like, you know, like at the end of the day, like all governments are corrupt. And the more government is involved in AI regulation, the worse it's going to be. You know, like even if they're trying to do something that's good, they just end up doing it. They just end up making it worse. So I don't know. It doesn't make me, doesn't give me solace when I see the government getting increasingly involved in AI stuff, you know? I think it's just a matter of time before the SWAT team comes to my house and like arrests me on stream for promoting reading papers and freely sharing information, but I don't know. All right. AI tools like SciSpace? I don't know. I don't know what SciSpace is. Any recommendations for starting new research on ML and protein design and drug discovery? I'm not much of a protein guy. I think you should probably read the latest AlphaFold. I think there was one that recently came out, right? Or there was ESM3. Is that what I'm thinking about? Yeah, ESM3. This is like the new meta paper where they basically train a giant protein model. Hoopo ranting is the best part of his sessions. I appreciate it, man. All right, I'm going to end it there. Thanks, Khalil, Aries, Nima, Swati, Ed, 87, Yair, Hijups, Aditya, Ed, Nora, Ogum, Roby, Hubes, Snooks, Julien, Vivek, Amelie, 770, Leroy. Who else? Leroy, DM2 whatever, Tacedon, Data Titan, Majetti, Quarant Duz, Eli Kate, and Sotaki. Thanks everybody for hanging out. Hope you guys have a great time. Have a great weekend and see you guys later.